This is a short video on the capabilities of the Michell Hydrodynamics Laboratory at the University of Melbourne. My name is Jason Monty and I am the director of the laboratory. We have quite a number of people working in the laboratory. We have 8 academics, including academics from the Fluid Mechanics group in Mechanical Engineering and the Ocean Engineering group in Infrastructure Engineering. Altogether, we have 11 postdocs and PhD students working in the lab full-time. The first facility I will introduce you to is the tow tank. This facility has been in place since the 1960s, but we refurbished it significantly. In this video that I am showing you now, which is available on YouTube by searching Melbourne boundary layer, you will see some schematics of this tow tank. It is a 60-metre long tow tank and it has a carriage that is fully automated that moves up to 3 meters per second. The carriage position is very accurately known to within 0.1 millimeters at any point during its travel. In this particular video, we are looking at a flat plate being towed past a stationary imaging system. The flat plate is designed to simulate the bottom of a flat bottom ship. In this video, you will see a simple flow visualization of the turbulent boundary layer developing underneath a ship hull. You will see that the boundary layer grows as the ship goes by, entraining more fluid from the free stream, which you see in black. This is just an example of the kind of imaging we can do. Using that imaging techniques, we can do particle image velocimetry as well, which I will describe a little later. One of the projects that we are working on in the tow tank is to look at the far wake of underwater vehicles, and this is funded by the Office of Naval Research Global. The idea is to analyze the far wake, which is the wake generated by a submarine cruising at depth very far downstream, hundreds of diameters downstream. And we can also determine the interaction of this far wake with the surface. Using our stationary imaging system, we can do PIV on a body moving past. As the body moves past our stationary window, we observe the wake developing in time. That is, the wake grows in time. By stitching together the images at different times, we effectively get the development of the wake with streamwise position. Using this technique, we can achieve very far distances downstream. So we can analyze the far wake at up to 600 diameters. If we scaled this up to a real submarine, that would be over 6 kilometers downstream of the submarine. This has never been achieved before and is impossible in wind tunnels. Recently, we have built a wind tunnel on top of this tow tank. And as you'll see through these slides, the beautiful thing about this wind tunnel is the design of the entrance. We have a contraction that accelerates the air coming from the fan and a ceiling which contains the air. The ceiling is removable. As the air is accelerated through this contraction, we then have a flap which allows the air to come through over the water surface in a uniform stream with low turbulence and parallel to the water. This is unique to our facility. The wind speeds that can be achieved are very high. We can get up to hurricane speeds of 150 kilometers per hour. Here's a short video showing you the real facility. You can see the removable ceiling panels that are framed in wood and made of acrylic so we can see through them. This allows us to see the development of the waves. Now you'll see inside the facility, you can see the development of the waves purely generated by the wind, which looks a lot like the ocean surface. At the other end of the facility, we have our stationary imaging system. This imaging system consists of PIV equipment, that is, a laser, optics, and cameras for doing particle image velocimetry. An example of these particles in the water are shown as a wave passes by. This is a particularly strong braking event which generates lots of bubbles, but you can also see at the bottom of the image the particles in the fluid. By tracking these particles in time, we can get velocity fields, and there are 3 examples shown here. These are the streamwise velocity fields below waves. And then from that velocity information, we can determine statistics such as the dissipation. This graph shows the dissipation and how it changes with depth. This data was published in the Journal of Physical Oceanography in 2016. The nice thing about this result is that if we look at field data shown on the right, published by Sutherland and Melville in 2015, you can see that the trends in the field are very similar to what we saw in our simplified laboratory study, proving that braking waves are the dominant mechanism of turbulence production and dissipation in the real world. The second facility I will introduce you to is the sea ice wave interaction facility. This is a tow tank that is housed, a wave tank that is housed in a refrigeration room that is 15 meters by 2.4 meters by 2.4 meters. The wave tank itself is 14 meters long, and we can generate waves up to 3 Hertz. The temperature of the air can be reduced to -12 degrees, which allows us to freeze the surface. Here's a short video showing high-frequency waves generated by our custom wave maker. The custom wave maker consists of a servo motor driving a linear actuator, so we can do computer-controlled waves of any spectrum. This video shows the interaction of waves with us. So you can see waves coming up to a frozen particle. In this case, the frozen entire surface. You can see the waves coming up to us. The last sheet is vaporizing as the waves decay as they go through the ice. We can also study small sheets of ice, as we can make ice outside in a smaller freezer and bring those sheets inside. Recently we completed the construction of a wind tunnel over the water, which allows us to study the ice-wave interactions in the presence of wind. This is the only facility in the world with these capabilities. Finally, 2 other professors at the university have facilities that I have not shown you inside the Michell Hydrodynamics Laboratory. Those facilities are for stratified turbulence, including oscillating grid facilities, particles in turbulence, including a swirling pipe flow, and also we have a water channel, Australia's only molecular tagging velocimetry setup, and we can also study polymer laden flows.